Welcome to this explainer. Okay, let's just address the elephant in the room right away. If the phrase rational algebraic expressions makes you instantly want to run for the hills, honestly, I totally get it. It sounds incredibly intimidating. But please don't panic. Today, we're going to completely demystify this little corner of algebra. I promise you, by the end of our time together, you're going to see that algebra is really just a friendly disguise for things you already know and use all the time. Our goal here isn't just to memorize a bunch of rigid steps to pass a test. We want to actually understand the fundamental logic underneath it all. So let's just take a breath, peel back the layers, and make sense of this math together. It's going to be fun. Here is our roadmap for today. Section 1, we'll meet the expression. 2, we'll cover the golden rule. 3, we go step by step. 4, adding and subtracting. And finally, Section 5, real-world algebra. Section 1, meet the expression. Let's figure out what these things actually are. Before we even think about looking at any letters or variables, I want you to take a second and think about the basic, everyday math that you use all the time. Think about slicing up a pizza, or dividing a restaurant bill among your friends, or figuring out a half-off discount at a clothing store. Fractions are literally everywhere. Take a look at the very simple fraction we have here, 6/8. You instantly know you can simplify that, right? Both the top and the bottom can be neatly divided by 2, reducing it down to 3/4. It's almost automatic. Now, take a look at the other expression, x squared minus 9 all over x minus 3. It looks a little intimidating, maybe, a bit like alphabet soup, but here is the absolutely crucial insight. They are the exact same concept, just dressed differently. One uses purely numbers, and the other uses variables, but the underlying logic to simplify them is absolutely identical. Math is really just a language, and today, we're simply translating it. Let's get the official definition on the table so we know exactly what we're dealing with. A rational algebraic expression is a quotient of two polynomials. Now, don't let the jargon throw you. Think of the word quotient as just a fancy term for the result of a division problem, which is almost always written as a fraction. A polynomial is just an expression with multiple terms. But here is the absolutely critical part that you have to remember. The denominator, the bottom part of the fraction, must not be 0. Why is this so incredibly important? Well, because dividing by 0 is mathematically undefined. You literally cannot divide a pizza into 0 slices. It conceptually breaks the rules of our universe. So for any of these algebraic expressions to actually mean anything, that bottom part has to be a non-zero value. Section 2, the golden rule. This is what you need to know before you cancel anything. Before you do a single calculation or even touch your pencil to paper, there is one supreme rule you have to remember. It's the absolute key to not getting completely lost. But before I just hand the answer to you, take a look at the question we have right here. Why should we factor first before canceling? I want you to take a mental pause here and really think about it. If you have a bunch of terms added or subtracted together on the top and some on the bottom, why can't we just start aggressively crossing out matching letters right away? It's super tempting, right? What happens if you try to take those kinds of shortcuts? Well, here is your answer, and it is the absolute golden rule of simplifying these expressions. Read it with me. Only common factors may be canceled, not separate terms. So the absolutely crucial point here is you cannot just cross out an x on the top and an x on the bottom if they are attached to other numbers with a plus or minus sign. Think of factors as sealed packages. If an x is sitting next to a plus sign and a 3, that plus sign is like thick, heavy-duty packing tape. It binds the x and the 3 together into a single, indivisible package, x plus 3. You can only cancel a package on the top if there is an identical, completely sealed package on the bottom. Please, whatever you do, don't fall into the trap of slicing open the box and crossing out individual pieces. Factoring is the tool that protects you from falling into that trap. Section 3, step by step. Let's walk through the actual simplification process. Having a reliable playbook prevents cognitive overload and really just guarantees your accuracy. So here is ours, straight from the lesson plan. Step 1, factor completely. We're going to look at both the numerator and the denominator and break them down into their multiplied parts, those sealed packages we just talked about. Step 2, identify common factors. We just scan the top and bottom to find matching packages. Step 3, cancel those common factors. Once we find the exact matches, we cross them right out. And step 4, write your new simplified expression. That's the whole shebang. 4 really straightforward steps. If you follow these sequentially and just take your time, you are never going to get lost. Let's put this into practice right now. We want to simplify x squared minus 9 all over x squared minus 3x. Okay, following step 1, we need to factor completely. Let's tackle the numerator first. X squared minus 9. Because 9 is a perfect square, 3 times 3, this is a classic pattern in algebra called the difference of squares. It always splits perfectly into a plus and a minus version of the roots. So it beautifully factors into the packages x minus 3 times x plus 3. Now for the denominator, x squared minus 3x. Both of these terms share an x, so we can just pull that x right out to the front, which leaves us with x times the package x minus 3. Now, take a moment to scan the top and the bottom. Do you see the common factor? You probably spotted it immediately. We successfully identified the sealed package of x minus 3 on both the top and the bottom floors. So, for step 3, we get to execute a highly satisfying decluttering process and vividly cancel that package out. Just cross it off. What are we left with? Just x plus 3 on the top and x on the bottom. We have our simplified expression, but hey, remember our early rule about the denominator? We absolutely must explicitly state that x cannot be 0 or 3. Why? Because if x were 0, that lone x on the bottom makes the whole denominator 0. And if x were 3, 3 minus 3 is 0, which again causes a total mathematical meltdown. Always protect the denominator. Let's see how this builds with our second example. Now this one looks slightly heavier. X squared minus 4 over x squared minus 5x plus 6. But don't worry, the exact same 4 steps work flawlessly every single time. Step 1, we factor. The top is another difference of squares. 4 is just 2 times 2. So that gives us the packages x minus 2 times x plus 2. Now the bottom is a quadratic trinomial, which takes a tiny bit of mental math. We need 2 numbers that multiply to positive 6. Actually, wait, those same 2 numbers also have to add up to negative 5. Let's think through that. Positive 2 and 3 multiply to 6, but they add to positive 5, so that's a no-go. What about negative 2 and negative 3? Let's see, negative 2 times negative 3 is positive 6, and negative 2 plus negative 3 is exactly negative 5. Perfect, hit the nail on the head. Therefore, our bottom factors into x minus 2 times x minus 3. Moving right along to steps 2 and 3, identifying and canceling our common factor. The matching package here is clearly x minus 2. Cross it out on the top, cross it out on the bottom. Now for step 4, we write our final clean answer, x plus 2 over x minus 3. And of course, just keeping things mathematically sound, we have to note that x cannot equal 2 or 3 to protect your denominator from hitting 0. Honestly, great job sticking with that process. Remember why this matters. We didn't change the inherent value of the original intimidating equation. Not at all. We just stripped away all the unnecessary mathematical noise. Section 4, adding and subtracting with same denominators. If you felt any anxiety welling up at the phrase operations on expressions, I really want you to take a deep breath. If you can add simple fractions, like if you know that 1/4 plus 2/4 gives you 3/4, you already have the exact skills you need to conquer this section. Check out this guided addition problem, 3y over y minus 5 plus 4y over y minus 5. Do you notice something great here? Because the denominators are exactly the same, they both have y minus 5, the heavy lifting is totally done for us. We don't change the bottom at all, we simply combine the numerators. 3y plus 4y gives us 7y. Put that over our common denominator, and our final answer is simply 7y over y minus 5. See? Nothing to it. Subtracting follows the exact same logical flow. Let's take a look at this one together. 10x over x squared minus 12 minus 5x over the exact same denominator, x squared minus 12. The denominators match perfectly. Just like swapping out blocks on a really sturdy foundation, we absolutely do not touch the foundation itself. We keep that x squared minus 12 comfortably resting on the bottom, and we just operate on the top pieces. 10x minus 5x leaves us with 5x, so our final elegant answer is 5x over x squared minus 12. Keep the common denominator, operate on the top. It's beautifully simple when you just maintain a measured pace and follow the rules. Section 5, Real-World Algebra. Let's look at some practical applications. All right, you have done the hard work. You've factored, you've canceled, you've handled operations. But let's validate everything we just learned and see how these tools actually live and breathe outside the classroom. Algebra isn't just some abstract academic exercise meant to torture you. It's incredibly practical. In entrepreneurship, you use these exact types of expressions to simplify complex formulas for cost, profit, and sharing resources. In science, calculating speed, time, and distance rates frequently requires simplifying complex fractional equations. And in financial literacy, understanding your interest payments or finding the true unit cost of an item relies heavily on this exact math. For example, if you're trying to figure out the real unit cost of a massive bulk purchase after applying some complex variable discount, reducing the rational expression tells you exactly what you're paying per item, almost instantly. It cuts through the fog. Let's build a really tangible scenario here. Imagine a small business owner mapping out a daily cost pattern for their store. Let's say X represents the number of products they sell, and 5X represents a fluctuating variable, like their shipping fees. The raw data gives them a really messy formula to look at. X squared plus 5X, all divided by X. Now, they could plug numbers into that complicated mess on a spreadsheet every single day, wasting valuable time, or they could use our 4 steps. They factor the top by pulling out the common X, giving them X times the package X plus 5. They see the common factor of X on both the top and the bottom. They cancel it out, and suddenly they realize their actual cost pattern is simply X plus 5. By taking 30 seconds to factor, they literally just save themselves hours of confusing repetitive math over the course of a year.
Which naturally leads me to this final thought. Simplifying an expression doesn't change its value. It changes its usability. It makes it work for you. So how can you apply these simplification steps to bring order and clarity to the complex problems in your own life? Just like in our algebraic expressions, real-world problems often look massive, tangled, and super intimidating at first glance. But if you take the time to step back, break them down into their smaller factors, find the commonalities, and just cancel out the unnecessary noise, you will find the core issue is usually much simpler and completely solvable. Thank you so much for joining me for this explainer. Keep factoring, keep simplifying, and I will definitely see you next time.